that's what I was telling you. But he was like, it's better if we do it.
Okay. All right, let's try this again.
That's never.
So today we need to talk a lot about how to experimentally determine the delta H for a reaction. The last couple of days we've been looking at theoretical determinations of delta H. We can use the heat of formation table. We can use the bond energies of all the bonds in a reaction. Or we can use Hess's law, as we learned yesterday. 3 different ways. Again, they're all theoretical. You don't have to put your hands on any chemicals to be able to determine the delta H of a reaction if you have those resources, the data tables. If you, though, need to do an experimental determination of delta H, then we're going to do a process that we call calorimetry. This is experimental, and it involves a reaction, or at least some measured, some measurement techniques. So we're going to talk about that today. Now, I had mentioned yesterday the zeroth law of thermodynamics. If you have 2 objects that are in contact with one another, in thermal contact, like they can exchange heat, then the warm thing is going to give heat to the cold thing, or the cooler thing, and that transfer will continue until they're at the same final temperature. So that the amount of heat that the cool thing gains is equal to the amount of heat that the warmer thing lost. This is going to assume that the objects, or the exchange of heat, is in a insulated container where it can actually be measured. That's going to be important. I did mention an equation yesterday. That equation was Q equals mc delta T. And just for the benefit of anybody that has not seen this before, I should have formalized this yesterday and I didn't. The m represents the mass. We're going to use this equation a couple of times today, so you're going to get the hang of what this is. The delta T is the change in temperature. Now, the change in temperature can be left in Celsius degrees. I know that I tried to indoctrinate you, use Kelvin, use Kelvin, use Kelvin when we're doing the gas laws. When you see a T term, you have to change the temperature to Kelvin. However, when we're doing a delta T calculation, it doesn't matter if you change it to Kelvin because the Celsius degree is the same size as the Kelvin degree. So delta T in Celsius will be the same as delta T in Kelvin. So you don't have to change to Kelvin if you have a delta T term. If you have an equation that just involves T, you have to use Kelvin, but not delta T. Now I saved this C for the last one. C represents the specific heat capacity. That is the term C here. Now every substance has its own C value. It's a property of matter. And I'll just mention this. The definition of specific heat capacity is the amount of energy, I'll say the amount of heat, required to raise 1 gram of a substance by 1 degree Celsius. So its unit is joules per gram degree Celsius. The unit kind of defines what specific heat is. It's the amount of energy in joules, heat energy, to raise 1 gram of a substance by 1 degree Celsius. So I will just mention that water has a high specific heat capacity. Water's is high. If you have done specific heat or mc delta T before, you might remember the specific heat of water. As soon as I say it, you'll be like, oh yeah, I've heard that before. If you've never heard it, obviously you wouldn't know it. Anybody remember what water is? Do you remember? 4.18. 4.18, yep. That's on the equation sheet. And I think it'll be given with an extra sig fig, it's like 4.184. But I'll just always use 4.18 joules per gram degree Celsius. Now, compare that with metals. All metals, I believe, are all 1, or not 1, less than 1. Metals' specific heat values are low, like less than 1. So we can see that compared to metals, water is extremely high. It takes a lot of energy. What that means to have a high specific heat, it takes a lot of energy to warm water up. Or when you need to cool water down, you have to remove a lot of energy from it. Metals, since they have a low specific heat, they're easy to raise the temperature or lower the temperature. It doesn't take much heat to change their temperature, but it does take a lot of heat to change water's temperature. So we'll use these values. In fact, our first example, I'll be showing you a calorimetry problem where we have to use this. Okay, so I keep using that term. Here is the slide that introduces calorimetry. Now I'm going to introduce calorimetry with a picture. We see often, there's more than one type of calorimetry problem or technique. There's actually, this is a completely rude term to use in chemistry, but one of the forms of calorimetry is called bomb calorimetry, like B-O-M-B, bomb calorimetry. And you see that term, you think, oh, I hope that we can do that. But bomb calorimetry is an expensive experiment. I actually did a bomb calorimeter lab in college, and it is totally anticlimactic. When you hear bomb, everybody thinks the same thing, right? But a bomb, in terms of calorimetry, nothing explodes. Why would they call it a bomb if it doesn't explode? It's a horrible name. So, yeah, a bomb is like a capsule that doesn't even expand or whatever. It's just disappointing. So it's a capsule that you put into water and you run an experiment with it, and everything is contained at the same volume. Normally in this class, not normally, you're not going to do anything with bomb calorimetry. It actually used to be a part of the curriculum for this class, but they've removed bomb calorimetry. You may even see questions, if you're just scanning through the questions in the exercises, you may see questions about bomb calorimetry. But anyway, we're going to be using something called coffee cup calorimetry. Now the reason it's called coffee cup is only because a coffee cup is meant, or is normally an insulated container. It's good to have an insulated container because that allows the contents of the insulated container to provide or to house the system and the surroundings, so that there's no interaction with any of the rest of the universe, just what's going on in the cup, the coffee cup. Oops, I just didn't mean to do that. Is all the exchange of energy that's happening. Now, in this class, we're going to use coffee cups that are like this. We could use styrofoam cups, and we used styrofoam cups for years, but we actually, several years ago, we got a grant to buy a set of these. And these are wonderful. These are much better than styrofoam coffee cups. A lot of times, kids would put their thermometer into the styrofoam coffee cup and then just let it go, let the thermometer go. And the thermometer is long, you know, and it would just be top heavy and fall over, and all the contents of the cup would fall out. The student would just look dumb. And so these are, you know, with that bigger, rounder base, heavier, and they insulate wonderfully. These are going to be the coffee cups that we'll use. So anyway, there's our insulated cup business. That matters. And the whole principle behind coffee cup calorimetry is this zeroth law of thermodynamics, which says that, oh, and I'm going to show you a picture of this as well. I think a picture helps. So in calorimetry, we have an insulated cup, and then of course there's water, and in the water is some vessel with a reaction happening inside of it. I don't know how to show, I'll just... RXN is an abbreviation for reaction. So you'll have some vessel inside of the water with a reaction happening inside of it. And it is possible that it's not even in some vessel, it may just be happening in the water, like dissolved things are reacting in the water. So what happens is, the reaction happens, and if the reaction is exothermic, it releases heat to the water, and the water warms up. If the reaction is endothermic, then it pulls energy out of the water, and the water cools down. So this is what the process of calorimetry is. We always will do calorimetry with a thermometer in the water. So we're monitoring the temperature of the water. And since we have this equation, Q equals MC delta T, it's always going to be easy for us to calculate how much energy the water gained or lost because of the MC delta T formula. And that will be, by this principle, Q of the water equals negative Q of the reaction. We'll be able to figure out a delta H for a reaction. So this is what I'll be showing you some examples of today. So of course we have a thermometer. In case my amazing drawing doesn't make sense to people, they'll be labeled. Okay, now there is an example down here on the bottom of the slide. I'm not going to have you do this example with me. We're going to go to the next slide. So let's go to the next thing here. This is not a reaction happening in water, but it's just an exchange of energy. And you will have exercises like this when you go to do them. Okay, so let's talk about this one. A 150 gram sample of a metal at 75 degrees Celsius is added to 150 grams of water at 15 degrees Celsius. So we have a hot metal. 75 degrees Celsius is quite warm. You probably wouldn't want to hold it in your hand. So it's put into cool water, water at 15 degrees Celsius. The temperature of the water rises to 18.3. This goes up by a couple degrees. Calculate the specific heat capacity of the metal, assuming that all the heat lost by the metal was gained by the water. This is the work of the insulated cup. There's no loss of energy to the environment. The system and the surroundings are all in the same container. And so that exchange of energy that's happening between the metal and the water is going to all be contained within this insulated cup. Okay, so what we have here is we have an exchange of energy. Now, one thing that we do need to understand is when you put two things together, one having a high temperature and one having a low temperature, and they're put into the same container, we would say that they're in thermal contact with each other. So what happens is the warm thing gives some of its heat to the cool thing. So it's going to cool down because it's giving some of its heat away. The cool thing warms up because it's having heat given to it, and that continues until the two are at the same final temperature. When they're at the same temperature, there's no more exchange of heat. They have reached what we call thermal equilibrium. It says up here that the temperature of the water rises to 18.3. So the water's down here and goes up by a couple degrees. That means that the metal started at 75, it goes down to 18.3. The two will always have the same final temperature. They won't have the same delta T, but they'll always have the same final temperature. So if you know the final temperature of one of the components of a thermal exchange, then you'll know the final temperature of the other one. They have to be the same. All right, so that's going to be handy for us. And remember that too, the same final temperature always. Well, that means this, that Q, the amount of water, sorry, I'll say that again. The amount of heat, Q, remember Q represents heat, E equals Q plus W. The amount of heat that the water gained is equal to the amount of heat that the metal lost. So I'm going to say QW, this is the amount of heat the water gained, is the same energy as the amount of heat that the metal lost. And that means that MC delta T for the water equals negative MC delta T for the metal. We don't have a reaction happening. We're not finding a delta H. We're just looking at a metal and it's getting rid of some of its heat. And the question is, what is the specific heat of the metal? That's what we're trying to find here. So it turns out that we know the mass of the water is given. We know the specific heat of water. I gave it to you a few minutes ago. We know the delta T of water. We can see the two temperatures. We know the mass of the metal is given. We know the delta T of the metal. Started at 75 degrees and went down to 18. So we have what we need. We can solve for the specific heat of the metal. Okay? So let's go ahead and finish that. That's really, we're good when we see that. The mass of the water. It turns out that the water and the metal have both the same mass. It's 150 grams. If you're math savvy, you just cancel those out. I'll leave them in there, but do look for shortcuts if there are any mathematical shortcuts. They do happen often. So anyway, well, let's go ahead and put the masses in. Mass of the water is 150 grams. Specific heat of the water is 4.18 joules per gram degree Celsius. the delta T of the water started at 15.0, went up to 18.3, so there's going to be a change of 3.3 degrees Celsius. And that's equal to the amount of heat that the metal lost. Now I'm going to make a comment. I want you to listen to this because you're going to start doing the homework exercises and looking at the solutions manual. And the manual and the book do something different than what I do. And it makes me crazy because the Zoom dolls, as good of teachers as they are, and really, you know, as the authors of the book, they're kind of your teacher this year as well. They do something that I don't approve of. They should have asked me, of course, but they didn't. They encourage you to keep all of your Q's positive. Even the metal, which clearly loses heat and has a negative Q value, it's perfectly fine to have a negative Q. There's nothing wrong with that. Mathematically, it makes sense because Q is the transfer of heat. So if something is losing heat, it should have a negative Q. Well, they're going to encourage you to keep the positive. So they're going to, in the solutions manual, it's going to say Q water equals Q metal. Physically, that's not true. It's the opposite because the metal's losing heat. Now, that means even this term right here, they're going to make positive, which means you see that the temperature of the metal is going down. It starts at 75 and it goes down to 18.3. They're going to have you take the absolute value of it. They're going to have you take 75 minus 18.3, which is wrong. The delta T of the metal is 18.3 minus 75. It's the final temperature minus the initial temperature. So why they're doing that, I just don't know. I don't see how that helps people. Yes?
We can still use it though.
Of course. Of course. Like I say, the Zoom dolls are kind of your teacher too. So yeah, I'm not, once you see it and do it like the solutions manual does, then I understand. I don't like it, but I understand and I'm fine. I don't seem fine, but I am. So anyway, we're going to do this the correct way, Ahmad. And I'm going to put the negative sign out in front of that Q of the metal. And we're going to have 150 grams of the metal now, times the C of the metal, which we don't know. We're going to try to solve for that, times the delta T of the metal, which is a negative value. What is it? Now keep in mind, 75 only goes to the ones place. So the 18.3, the 0.3 is not going to help when we do this subtraction. 18 minus 75, we have to round it to the ones place. I believe it's going to be negative 57. So that solving for C is very simple. Just get the C by itself and watch out for those negative signs. I believe, just from memory from first hour, the specific heat of the metal is 0.24. Anybody do that one? Thank you. So C of the metal is 0.24, and again the unit is joules per gram degree Celsius. The negative there cancels the negative there, so in the end, C always has to be positive. I just like to be consistent and always, delta T should always, delta anything should always be the final minus the initial. Notice, water has a high specific heat, it's 4.18. Metals have a low specific heat. If you're asked to find the specific heat of a metal and you get like 14, then your brain should say, hold on a second, this is not right. So yeah, metals are typically between 0.1 and 1 in their specific heats. Yes, Tara?
If you do it the book way, would the heat of the water plus the heat of the metal equal 0?
No. That's why I just don't like the book way. Because it wouldn't. These two things would be equal. The Q of the water would equal positive Q of the metal the book way. So you just have to know that the metal loses heat, but you can't show that mathematically. Happy Friday, sir.
Yep, you too.
Thank you. Anything else about this one before I move on to the next one? The next one will have a reaction happening. It's not an official chemical reaction. It really is more of a physical change, but it's a great example and we're going to use it. So the next example we have is going to be a reaction that happens in water. We have NH4Cl, ammonium chloride, solid, just simply dissolving into water. And as it dissolves, of course, it's an ionic compound, so it dissociates into ammonium ions and chloride ions. So our chemical equation is this one. Yeah, with a pink background. The highlighter tool doesn't work awesome, but we're using that reaction. Okay? So it says if 8 grams of ammonium chloride dissolves in water, determine the delta H. Now we're going to do this both experimentally and theoretically. So we'll do it experimentally first. Now the 8 grams, I measured some out yesterday and I didn't use 8 grams. It was 6 point something. So I'm going to have us all change the 8 grams. If you're following this, cross off the 8 grams. I've got samples in the back. We're going to use 6.58 grams. 6.5, I'll bring it up to the front. Okay, so yeah, we measured these out yesterday and I wrote down each tray how much ammonium chloride was in there. It's 6.58 grams. So, yeah, let's take a look at this. I have a coffee cup calorimeter. I have a sample of room temperature water. We're going to measure its temperature. And I have a graduated cylinder. Water really helps us out because water's density is 1. So when I just use a graduated cylinder and measure out 100 milliliters of water, it'll be 100 grams of water because of the density of water being 1. I'll leave it up here. If you don't trust me that I've measured out 100 grams of water, take a look. It's pretty close to 100 grams. I'm going to record it, the mass of water, as just 100 with a decimal. I'm not going to say 100.0. My eyes aren't even very good anymore. I can't see that well enough to know that the meniscus is right on the 100 line. So I'm just going to call it 100 with a decimal point, ml. Or no, it's got to be in grams because it's a mass. So the mass of the water is 100 grams. The initial temperature of the water, I'm going to go ahead and put it into my insulated cup. Okay, so now I have to take my, have you used these before? Everybody used these? Thermometers that don't have any numbers on them because they're Bluetooth connected to the iPad. I think I still have graphical analysis. So you're going to have to use this one, graphical analysis. And that was the curve we got last hour. Okay, so yeah, remember all this because we haven't used them in here. Maybe you have in GBE if you've taken that class. Turn it on so that it's blinking red. And then we need to pair the probe to the app. So just click Proximity Connect, and all you have to do is be close with your device to the iPad, and it'll pick it up within a few seconds. Okay, there we go. There we go. Okay, cool. Good. Okay, so down here in this little corner is the temperature of the air. It's reading the temperature, whatever the thermometer is picking up. Let's see, I'll keep this up here too. So putting the thermometer into the water, I took the water out of the tap about an hour ago, and let's see what it goes. Not exactly the same as room temperature, but it's pretty close. Okay. So the initial temperature, though, is still changing on me. Come on, hurry up. Oh, and I can't go off of it. Maybe it's going to be hung up on 22.9. Good. Just going to give it a swirl and make sure that is accurate. Okay, of course. It's going to change again on us, but we'll go with that. 22.8 is our initial temperature of the water. Okay, and the final temperature we won't know until the end. And let's see, the mass, we have the mass of NH4Cl. So let's go ahead and do this. Putting this whole 6.58 grams of the solid into the water. I'll try to do this quickly and get the lid on right away. Whoop. Now, we'll go back to this and collect, and I'll just give this a swirl. Another thing that's real nice about these Yeti style cups is just their functionality. We can just give it a swirl. We don't have to stir with the thermometer. We can just pick it up and swirl like this and not worry about it splashing out. You can kind of see that the temperature is going down. What does this say about the reaction? Is the reaction exothermic or endothermic? I heard both. The water's temperature is going down, so what does that mean about the reaction? It's taking in energy from the water. So the reaction itself is taking in energy. It's endothermic. Yeah. Now we can see, and you'll be using this app on Monday because you'll be doing a lab with the same equipment. This button right here with a little magnifying glass, that will zoom in. I mean, the temperature default goes from 0 up to 300. That's obnoxious. So clicking on that magnifying glass, that'll get us to something that we can see better and track better. So I'll just keep swirling this and watching that temperature. 18.4 it looks like. Well, maybe it's settled on 18.4. Looks like it's flatlined here. Good, I think it's fine. Okay. I will just make sure that all of the ammonium chloride is dissolved. Some of our measurements have chunks of ammonium chloride, but that's all dissolved. So, and that's not changing at all. So we're going with that. The final temperature is 18.4. TF is 18.4 degrees Celsius. Okay, now the zeroth law of thermodynamics says that Q of the water is equal to negative delta H of the reaction. The amount of energy that the water lost, and it did lose energy, is equal to the amount of energy that the reaction gained. So I get that from this right here. Q of the water equals negative Q of the reaction. Remember, when your system is a reaction, we call Q delta H. So I've made that change there. That's why I'm calling it delta H there. So we can determine what the delta H of this reaction is. Q of the water would be MC delta T. So the mass of the water was 100 grams. Specific heat of water is 4.18 joules per gram degree Celsius. Delta T of the water is that minus that, which is negative. Is that 3.6? Negative 3.6? No, it's not. It's 4.4. It's negative 4.4. Okay. So the water did lose heat. Its Q is going to be negative, and let's go ahead and calculate. Can anybody do that for me? Looks like we can only have 2 sig figs in our answer. And what do you get? 1800? Q of the water is negative 1800 to 2 sig figs joules. That means that delta H of the reaction has to be positive 1800 joules. Do you agree? Okay. So we use calorimetry. The amount of energy that the water lost is equal to the amount of energy that this process gained. The process of changing that solid into the dissolved ion. Now, here's the fun part. We're going to do this theoretically. Theoretically, we can use the appendix in the book. Ronan, you're elected because you're closest to the books. Would you grab a book for us? And go to the appendix, page A20, A21. This part's going to be cool. And so what we're doing is we're going to look up the heats of formation of our reactants and products. We're going to find delta H for this reaction.
A20?
Yeah, A20, A21. Okay, so we're going to have to look up the heats of formation of ammonium chloride. It'll be on the right side on page A21. The nitrogen compound. Find solid ammonium chloride's heat of formation.
Ammonium chloride?
Yep.
Negative 314.
Okay, and close to it should be just the ammonia, not ammonia, ammonium ion, aqueous. NH4 aqueous.
Negative 132.
Now, on the previous page is the chloride ion. Look in the chlorine group.
Negative 167.
Okay. Thank you. Now, what is the unit at the top of the column for the delta H? I didn't put the unit on any of these, but we'll make sure that we know what they are.
Delta H degree F.
Yep.
Kilojoule per mole.
Those are kilojoules per mole. Thank you. Thanks for doing that. And we're good with that. We don't deal with it anymore. Okay, so theoretically, we can find the delta H of this reaction. We're going to do delta H equals products minus reactants. That's going to be the products, negative 132 plus negative 167 minus the reactants, negative 314. All right. Now what do we get? Can you do this math? Negative 132 plus negative 167. And all the coefficients, by the way, are 1. So this should be accurate. Assuming Ronan's eyes aren't crossed and he read the wrong thing. Let me look at you. Look at. Oh, his eyes look good.
Very good.
15. We get a value of positive 15. How did we do? Experimentally, we see that the delta H of this reaction is positive 1800 joules, which is 1.8 kilojoules. Theoretically, using the resource that I tout as the reliable resource for delta H values, the heat of formation table, it gives us a delta H of 15 kilojoules. So experimentally, we got 1.8 kilojoules, and theoretically, we got 15 kilojoules. How'd we do? Okay, now let me ask you this. Is it accurate to compare this value to this value? Remember what the unit up here was? I asked Ronan specifically for the unit. What's that say? Kilojoules per mole. Did we dissolve a mole of ammonium chloride? We didn't. We need to do a correction for the amount of ammonium chloride that we actually dissolve. Now, I do this, and this is really important for you to see. You can include the delta H value as a part of the stoichiometry conversion. So we know that only 6.58 grams of ammonium chloride, that's not a mole. We're going to take that value, 6.58 grams of NH4Cl, and we need to change it into moles, which means we're going to convert, there's 1 mole of NH4Cl for every molar mass of NH4Cl. 14 plus 4 is 18, plus 35.5, 53.5. That's actually about 1/10 of a mole or so. So anyway, but look at this next conversion. We got to moles of ammonium chloride, and I want you to know that for every 1 mole of ammonium chloride that dissolves, 15 kilojoules of energy are taken in. So that is a conversion factor. You can actually use the delta H of a reaction as a part of a stoichiometry conversion. So it's positive 15 kilojoules for every 1 mole. And this calculation is going to give us what the theoretical delta H was for the amount of NH4Cl that we used in the reaction. Now I want you to calculate that. 6.58 divided by 53.5 times 15. Say it again. Everybody catch that? 1.8 kilojoules. This is where we drop the mic and walk off the stage. What just happened? Experimentally, you saw what I did. I measured everything, and you measured it with me. We had 1,800 joules for our delta H. Theoretically, using that, what I call the reliable resource for delta H values, we get the same exact thing, experimentally and theoretically. What does that tell us? 2 things. Number 1, the book values, those heat of formation, they're good. It works. Second thing is, this equipment works, and it works beautifully. So we do really trust calorimetry, the process and the equipment that we use, that it is accurate and that it is reliable. So yeah, man, I love doing this exercise because with careful measurements, you can get right on. Experimental and theoretical, it's a beautiful thing. Okay, so let's see, how are we doing for time? Not very well. So that was chapter 6. Now I've shown you everything I want to show you in chapter today. You good there? You may have noticed that the book gives us not only questions and homework exercises from chapter 6, it also gives us chapter 10 exercises. I haven't talked one word about chapter 10 yet. Well, I've got 15 minutes. Let's talk about chapter 10 in 15 minutes. Actually, there's 16 minutes. We got plenty of time. Okay, so chapter 10, and we're not doing the entire chapter 10. All we're doing is we're looking at when a substance changes temperature, how much heat is involved. And that uses Q equals MC delta T. But it's also going to deal with when a substance changes physical state, like when water freezes, or when water boils, or when ice melts. Those kinds of things. How much energy is involved with those? Okay, this next slide is going to be a chapter 10 slide. In fact, it's the only one from chapter 10. I've got chapter 10. What I need you to know is just all wrapped up in one slide. If a substance changes temperature and we want to know how much energy is involved, we use Q equals MC delta T because that temperature change is built into it. So for temperature changes, we're using MC delta T. However, if the substance is not changing temperature, but is still taking in heat or getting rid of heat, that must mean it's undergoing a phase change, a physical state change. Now, you may or may not know this. Most of you do know this, but you may have never heard of it before. You probably did in Chem 1 though. If you take a thermometer and stick it into water, and then you start heating the water of course is going to raise in temperature, and the thermometer is going to show you that. It goes up and up and up and up until it hits the boiling point of water. What does the thermometer do when you hit the boiling point? Yeah, I see what your hands are doing. Exactly. Boom. It just goes like that. The temperature stops changing. It sits right on 100 degrees the whole time the water is boiling. You can crank up the heat as high as you want. While the water is boiling, its temperature is stuck there at 100 degrees. All of the heat that you're putting into it is going to changing the physical state, not changing the temperature. The same thing is true when water freezes. If you take a cup of water and stick a thermometer in, stick it in the freezer, you'll see the temperature go down, 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 down until it hits 0. Then when it hits 0, it flatlines. It just stays constant while the physical state is changing from liquid to solid. Once it is all turned to solid, you got your whole cup will be solid, frozen around the thermometer. Then the temperature starts going down again. But during a phase change, the temperature doesn't change. So that's what I'm talking about here. Phase change means physical state change. The temperature's not changing. So if we want to know how much energy is involved with the phase change, we can't use Q equals MC delta T because there's no delta T. It doesn't change temperature during the phase change. So there are other equations that we have to use. They're really the same equation, but they use a different constant. So if you are melting a solid, then we're going to use this. And let's see. Yeah, it says for melting. Q equals the enthalpy of fusion times moles. So this is a very simple formula, and it says that when you're melting a solid, the amount of heat involved with melting a solid is going to depend on what the heat of fusion of that substance is. Every substance has its own heat of fusion, just like every substance has its own specific heat. So I'll tell you what water's heat of fusion is. That's when you're going to use the most. And if they give you a different substance, they'll give you the heat of fusion for it because it won't be the same as water. A couple of things about this. Let's do the water first. The delta H fusion of water equals 6.01 kilojoules per mole. So if you melt a mole of water, which is 18 grams of water, you need to put in 6 kilojoules of energy to get that 1 mole of water to change. No temperature change happens there, it just goes from solid to liquid. The other thing I was going to say was this equation is also used for freezing. When a liquid freezes, that's the exact opposite of a solid melting. So it's the same equation, but with a negative sign. Because when you freeze something, you have to remove energy from it, right? So this is the same equation for freezing. But opposite sign. So do be aware that melting, freezing are opposite processes. They involve the same amount of energy, it's just whether the energy is going in or if you're taking the energy out is the difference between melting and freezing. Okay, now if a liquid is boiling, then we have to, it's the same equation like I said. However, it uses a different constant value, so I'm just going to break it up and make it a different equation. Q for melting is going to be determined by this simple calculation, the heat of vaporization times mole. The heat of vaporization of water, delta H vap of water, do write these values down. If you're not writing anything down, keep these down. You're otherwise just gonna have to go looking for them. It's not like you're gonna be in big trouble. But it's handy to just have them here. 40.7 kilojoules per mole is water's. The reason the water is significantly bigger vaporizing compared to melting is it's like 6 times more for vaporization. It's not about the temperature of it. You might say, oh, it's because of the higher temperature. No, we're just talking about the process itself, not about the temperature change. But yeah, to vaporize water, you have to completely break the intermolecular attractions. The particles have to completely come apart from each other. That takes more energy than just breaking the crystal structure. As a liquid, the particles are still close to each other. But yeah, when you go from liquid to gas, it takes a lot more energy to totally break the particles apart from each other. So any substance is going to have a higher vaporization heat than fusion. The word fusion is a word, it's an old word. Back in the day, they used to refer to fusion as melting. It's just the heat of melting is all it is. But fusion, we don't use that word anymore for melting, but that's the scientific meaning of fusion, is melting down. Okay, of course this would be the same for condensation of a gas to a liquid, but with the opposite sign as well. So how am I doing for time? Oh, we're doing great, we got like 10 minutes. I have a horrible, disgusting problem that I want to do with. It's not very nice for an old guy to say that to Tina. Hey, I got a disgusting problem. No. The problem was actually given to us by the Zoom dolls. It's in the book, chapter 10, number 99. Sometimes I wonder, do the Zoom dolls sit there at the dinner table laughing about the problems they come up with for you guys to do? I do wonder. I picture the Zoom dolls sitting, eating a nice juicy steak or whatever because they're filthy rich from selling all these books, and say, Stephen will say, Susan, you won't believe the problem I came up with for the kids to do this time. And this would be one of those. So it says, it looks harmless enough. What quantity of heat, we're going to have to calculate Q, is required to raise 500 grams of water, oh good, there's a mass, of ice, not water, it's ice that we're starting with, from negative 20 all the way up to 250 degrees. And of course, it's going to undergo phase changes as it does this. Susan must, Stephen, you got a good one there, right? Here's what we are required to do in this problem. We have 5 different Q's we're going to have to calculate. Because, and you might say, well, here's what we have going on. We have ice that we're starting with at negative 20 degrees. We start heating ice, and it goes from negative 20 up all the way, it just keeps heating up until it gets to 0. When it gets to 0, it starts to melt. So then all the energy that we keep putting into it now is not changing its temperature, see the flat? It's changing its physical state. Once it's all changed, now it's a liquid, and it starts rising again. But then it gets to 100 degrees and it starts to boil. And boils, until it is all boiled. Now it's all steam. And the steam has to be raised to 250 degrees Celsius. 5 different Q's. Now you might think, oh, we can be efficient with this all of our temperature changes, we could just combine those. Nope. You can't do that either. Now, I haven't told you this, you may know, but not for me. The specific heat of water as a liquid is 4.18. That is not the specific heat for ice or steam. So that means, and I'm going to write this down for you, you might want to have it down as well. Carbon. I put a C in and say carbon. The specific heat of ice is 2.1 joules per gram degree Celsius. The specific ice, jeez, I think I need a snack. The specific heat of steam or water vapor is 1.8 joules per gram degree Celsius. Thank you very much. All right.
On the quiz, would we have to memorize it? Or
No, you'll be given those values. I believe, I don't know if these are on the equation sheet, but if I have you use those on a quiz or test, I'll give them to you. 2.0? Does it? I thought it was like 2.06. All right, so anyway, yeah, I mean, use whatever the book gives you. Okay, so we have 1, 2, 3, 4, 5 Q's. How about that? That we're going to calculate individually and then add them all together, and that'll be our answer. And for goodness sakes, be careful. Now I got lots of room down here. I'm going to go ahead and just do these 5 calculations down at the bottom. How am I doing for time? Not very well for time now. I thought I was doing fine until right now, and now I'm thinking, okay, we really need to hurry. So here's what it is. For the ice, we have a temperature change. We're going to calculate it with Q equals MC delta T, so the M is 500 grams. The C of ice is 2.1. And the delta T of the ice, while it's in the solid phase, is 20 degrees. It started at negative 20. It's ice until it gets to 0 degrees. So that's a 20-degree temperature change. That's Q1. Q2, the ice melts. So Q2 is heat of fusion, which is 6.01 kilojoules per mole, times moles. Now the problem doesn't give us moles, it gives us 500 grams of water. So we have to change it into moles. I'm going to do it like this, 500 grams over 18 grams per mole. I'm taking a little shortcut to save room and time. Should be 18.0. I'm just leaving it as 18. The reason I say that is because all these should have 3 sig figs at the end. Okay, that gives us the amount of heat to melt the ice. Now we have liquid water, so we'll just say water. Goes from 0 to 100 degrees. Q3 is 500 M, 500 grams, times C, liquid water, 4.18 joules per gram degree Celsius. And then delta T is 100. We get an answer for that. The next we have the water boiling. It's Q4. The heat of vaporization, 40.7, times the moles, which is like I did in Q2, 500 converted to moles, and it's divided by the molar mass, 18. We're getting there quickly. Finally, we have the steam. That's a temperature change. So we go back to MC delta T. The mass is 500. The C is steam now, it's 1.8. The delta T of steam, it goes from 100 up to 250, which is a change of 150 degrees. We did it. Now notice one other quick thing. The MC delta T, the energy you get from those is going to be in joules. The Q2 and Q4 with the melting and the boiling, those are going to be in kilojoules. So when you add them together, you have to have them all in the same unit. I would say all 5 of them, when you calculate them, get them into kilojoules. It's going to save you 3 digits, and it's just obnoxious to keep things in joules. So you use kilojoules for all these. So when you do Q1, Q3, and Q5, divide by 1,000, get into kilojoules. From my memory, I believe the final answer is Q total is 1660, I think. Is it 1680? Thank you guys. So, yeah, there's the whole thing. Oh, there's plenty of time. Anybody have any questions about any of that? Now, with that one example, you should be able to do the rest of the questions. In chapter 10, they'll involve phase changes and temperature changes. You just have to separate those out, calculate different Qs for the different processes. You may have to have multiple Qs in the same problem because you'll have a temperature change and a phase change, like we did here. Thank you for your attention to that. Yay for calorimetry.